Hello, this is the 12th video on my multivariable calculus course. So in this video, we're going to talk about partial derivatives. So in this course, we have talked about functions of several variables. We talked about limit and continuity in the previous video. In this video, we're going to start talking about derivatives. So unfortunately, derivatives in for functions of multivariable are much more complicated to deal with. But let's start with what we did for functions of one variable. So if you have a function of one variable, the way we define derivatives at some point, maybe x naught, is we take a point x close to that x naught, we evaluate the average of this, average rate of change. If this is y equals f of x, then the derivative at this point x naught is evaluated by taking the limit of rise over run. And that gives us the slope. As x approaches x naught, it gives us the slope. So this is rise and this is run. As x approaches x naught, it gives us the slope of the tangent line at this point to the curve. Now, if we are dealing with a function of two variables, then the graph would be in 3 dimension. And looking at the graph, we will be able to travel along this surface in many different directions. So what that means is that steepness or the slope along this surface would be different if you travel along the surface in this direction or in this direction or in this direction. So steepness here or here or here, these could be completely different numbers. So how do we define derivatives then? Well, what we can do is we can fix one direction and then we can evaluate the derivative in that particular direction. Two particular directions that are easier to deal with are x direction and y direction. So let me graph this one here and we will do the definition of partial derivatives and then we will do some examples. That's basically what we're going to do in this lecture. So let's just start from a point x naught comma y naught, and let's look above this point on the surface. This is z equals f of xy, and we are going to look at the direction of the y-axis. So in the direction of the y-axis, we are going to have a curve like this. In the direction of the y-axis, x naught is fixed. So this is the plane that we're looking at. The plane that we're looking at is x equals x naught. Now we are going to take a point close to x naught, y naught. Well, x naught remains the same because it is on the plane x equals x naught, and then y. Now for this curve, we're going to find rise over run. So what is rise? Rise is this guy minus this guy. The first one is f of x comma x naught comma y, and the second one is f of x naught comma y naught. So if we subtract these two, we get the rise, and then run is y minus y naught. So we are going to have to take the average rate of change in the direction of the y-axis. So this would be rise, which is f of x naught comma y minus f of x naught comma y naught. That's rise over run, which is y minus y naught. So this is the average rate of change. Now, what is the instantaneous rate of change? It is taking the limit as y approaches y naught. That is called the partial derivative. And the notation is this. Partial derivative of f with respect to y at x naught y naught is equal to limit as y approaches y naught f of x naught comma y minus f of x naught comma y naught divided by y minus y naught. And that's the notation for partial derivative of f with respect to y. So that's the notation. Another common notation that people use is by Greek d. So this is the same as f sub y. These are two different notations. There are other notations, but I'll stick to these two notations in this class. So if I were to do the partial of f with respect to x at x naught y naught, which is the same as f sub x naught y naught, what I do is I take the limit. This time I'm fixing y, so it would be f of x comma y naught minus f of x naught comma y naught divided by run, which is x minus x naught. So this is the definition of partial derivative with respect to x. So how do we evaluate partial derivatives? Well, to evaluate partial derivatives, to evaluate f sub x, we consider the other variable y constant and differentiate with respect to x. So if you have a function of three variables, then you do the same thing. If you have three variables, then you consider y and z constant and differentiate with respect to x. So for functions of three variables, if I'm evaluating f sub x at x naught, y naught, z naught, the limit definition is going to be the limit as x approaches x naught, f of x comma y naught comma z naught minus f of x naught comma y naught comma z naught divided by x minus x naught. So this is the partial derivative of f with respect to x at x naught, y naught, z naught. Okay, so now that we understood what partial derivatives are, we're going to look at some examples. So here is the first example. Evaluate f sub x at 1 comma negative 1 and 0 comma 2, f sub y at 0 comma 2. So let's look at f sub x. In order to differentiate this one with respect to x, we'll have to fix y. So this would be 3x squared y plus 2 plus 0. And f sub y, we are going to consider x constant. So that would be x cubed plus 0 plus 2y. So this would be the partial with respect to y. Now we are going to plug in 1 comma negative 1. We are going to get 3 times 1 squared times negative 1 plus 2. So that would be negative 1. F sub y at 0 comma 2. We are going to put 0 for x and 2 for y. So that would be 4. Okay, so let's move on to another example. If you look at this example, this function is given as a piecewise function. So we can't really evaluate partials of this function at 0, 0 by simply differentiating and plugging 0, 0. So for this one, we will have to use the limit definition. So f sub x 0, 0, that's equal to the limit as x approaches x naught. So just using the definition, f of x comma 0 minus f of 0 comma 0 divided by x minus 0. So in this example, this one is x naught, this one is y naught. So this would be y naught, this would be y naught, this would be x naught, and this is going to be x naught. Now we are going to simply plug in the values into here and we are going to take the limit. So this would be x approaching, so x naught is 0, so I'll have to change that to 0. F of x comma 0, because xy is not 0, 0, we'll have to use the first condition here. So that would be x to the fourth times 0 plus 0 cubed over x squared plus 0 squared minus f of 0 is 0 divided by x. Now if we look at this, we get the limit as x approaches 0. Well, the numerator is going to be 0, the denominator is going to be x, so this is 0 over x and the limit is 0. So partial of f with respect to x at the origin is exactly 0. Let's look at the same thing in the direction of the y-axis. So f sub y at 0, 0. So this is the limit as y approaches 0, f of 0 comma y minus f of 0, 0 divided by y. So that would be the limit as y approaches 0. So bottom is y. Well, top is f of 0 comma y. So I have to plug in x equals 0. So 0 to the fourth times y plus y cubed over 0 squared plus y squared. That's f of 0 comma y minus f of 0, 0, which is given as 0. And if we simplify that, we get the limit as y approaches 0. The first fraction is going to be y cubed over y squared divided by y, which is exactly 1. So f sub y of 0, 0 is going to be 1. So as you see, partial with respect to x and y are completely different numbers. Okay, so now given a function, we can also look at second partials of that. So if you look at a function f of xy, we have two first partials. We have f sub x and f sub y. But then we can take the derivatives of each one of these. We can take f sub x and take the first partial of this one and first partial of the first partial. So those are the second partials. And we can take f sub y and take the derivative of that with respect to x or y. So there is also another notation that we use for second derivatives, which is, if you look at this one, this is the second derivative of f with respect to x. The notation for this one, you have to be a little bit careful. The notation for this one is a little bit different. So this one, partial differentiation with respect to x comes first, so that would be on the right, and partial with respect to y comes on the left. So notice the order is different. X is on the left here, it's on the right here, y is on the right here, and it's on the left here. And that is how it would make sense, because that's partial with respect to y of partial of f with respect to x. The next one, f sub yx, that's the second partial of f with respect to x, with respect to y first, because y is on the left, and then with respect to x. So that would be partial with respect to x of partial of f with respect to y. And this one can be written as second partial of f with respect to y. Let's look at an example for second partial derivatives. So we want to find all second partial derivatives of this function. So we're going to evaluate first partial, and then we're going to go ahead and evaluate the second partial. So first partial, we'll have to use the product rule. So derivative of the first one is e to the x times the second one plus e to the x times the derivative of the second one, which is minus sine xy. And then we'll have to multiply that by the derivative of the inside, which is y. So that's first partial of this with respect to x. First partial of that with respect to y would be e to the power of x is a constant. So that would be negative sine xy. And then we'll have to multiply by the derivative of inside, which is x. Next, we're going to have to take the partials of these partials. So f sub xx, I'll have to take the derivative of this one with respect to x. So that would be e to the x cosine of xy plus e to the x minus sine of xy, and then multiplied by y, plus, we're going to use the product rule again, e to the x minus cosine of xy, and then multiplied by y squared, plus e to the x minus sine of xy times y. So that's the first partial of f sub x with respect to x. Now we'll have to take the first partial of that with respect to y. So there's only one y in the first one, in this one. So this would be e to the power of x minus sine of xy times x. The second one we'll have to use product rule. So minus e to the power of x cosine of xy times x. So that's the partial, that's the derivative of this one with respect to y. So that would be cosine of xy times x. And then minus e to the power of x sine of xy, and then derivative of y is just 1. Next, we're going to find the derivative of the second one, derivatives of the second one. So f sub y sub x, that would be the second partial of f sub y with respect to x. So that would be product rule again, e to the power of x times negative sine of xy times x plus derivative of the second one, which would be minus cosine of xy times y times x. I'm using product rule again, minus sine of xy times x. And finally, I'll have to take the derivative of this one with respect to y. That would be the last partial. So there's only one y here, so we don't need any product rule, we will get minus e to the power of x times x cosine of xy, and then derivative of the inside with respect to y, which is x. So we get x squared here. Now, if you notice the partials with respect to xy and with respect to yx, these two terms are the same. This term and this term are the same, and this term and this term are in fact the same. So what does that mean? It means for this kind of random function that we looked at, the partial is in fact the same. So I think I forgot an x here. So if I took the derivative with respect to y, I will get, no, I don't have an x here. But for this one, yeah, I don't have the x right here. Yes, I don't have that here. So these two in fact match. These two in fact match. So what we have is f sub xy and f sub yx in fact are the same. This is in fact going to happen for a lot of functions. With one simple condition, this order of differentiation doesn't matter. In fact, in this class, for all functions, this would happen. So here's the theorem that tells you that fact. So f sub xy is the same as f sub yx as long as both of these second derivatives are continuous, which would happen for all of the functions in this class. So let's do one example. Let C be the curve of intersection of the paraboloid z equals x squared plus y squared. So we have this paraboloid, and then we take the intersection of this paraboloid with plane z equals 1, x equals 1. And if we look at that, we'll get a parabola here. And the question is find the equation of the line tangent to this curve at 1, 1, 2. So tangent to this curve at 1, 1, 2, that's what we are trying to find. So if you look at the plane is x equals 1. So the tangent would be on the same plane. So the x coordinate is always 1. We'll have to find the y and z coordinates. So what is the slope? Well, slope would be partial of z with respect to y. That would be the slope. Because we're looking at the zy plane, basically, a plane parallel to the zy plane. So that what is that? That would be 2y. Now we're going to plug in the point that they gave us at 1, 1, 2. We will get the slope is equal to 2 because we'll have to plug in y equals 1. So we get the slope is 2. So now with the point slope formula, we can write down the equation of the line. We get z minus z naught, which is 2, equals slope times y minus 1. So equation of the line that they gave us is going to be z equals 2y, and the negative 2's cancel. So the line would be x equals 1 and z equals 2y. So this is the equation of the tangent line. Okay, let's do one more example on partial derivatives. So this one is an example in 3 dimensions, so function of 3 variables. We want to find the partial of this function with respect to x at the origin. So since the function is given as a piecewise defined function, we will have to use the limit definition. So this would be f of x comma 0 comma 0 minus f of 0 comma 0 comma 0 divided by x minus 0 by definition. Now the rest is plugging the values in here and taking the limit. So we're going to plug in x for x, 0 for y, and 0 for z. So we get x cubed plus 0 cubed plus 0 to the power 4 divided by x squared plus 0 squared plus 0 squared minus f of 0, 0, 0. F of 0, 0, 0 is obtained from the second condition divided by x. So let's simplify and then take the limit. Numerator becomes x. Denominator is also x. So the answer is in fact 1. So f sub x at 0, 0, 0 is in fact 1. So to summarize what we did in this video is we talked about partial derivatives. To evaluate partial derivatives, we have to treat all of the other variables constant and then differentiate as usual. If your function is given as a piecewise defined function, then you'll have to use the limit definition. And finally, for all of the functions that we're dealing with in this class, order of differentiation does not matter. I will see you in the next video.